type this into a list.
Let me get my calculator.
So put this set of numbers, the set of numbers that I had here, put it in the list. Once you put it in a list, do the 1 bars stat stuff for that list so that we can find the mean, standard deviation, and all that stuff. Is this 3.2?
Oops. Got it.
All right, something's not right here.
Jenna, did you do 1 or 2?
What?
She did
I did
one.
one.
That's the problem.
You're supposed to do two.
I did, oh, I did only do one. Never mind, I thought I did two.
Has everybody got punched into a list?
Yeah.
Somebody tell me what X bar is.
3.5.
Somebody tell me what standard deviation is.
2.29.
Everybody agree with that?
Yep.
You didn't just punch that into your calculator to find it.
Yeah, all right, that's not,
You
yeah. I did.
Oh my goodness.
Well, I didn't think about it till.
You having a rough day today? You got a game today?
Yep.
Yeah.
Oh my goodness.
Have you ever watched
Senior
play
night.
basketball?
That worries me if you're having that rough a day in here. You're gonna foul out in the first quarter.
Probably, I wouldn't put it past me.
Yeah, we're all gonna cry.
What we're going to cover today. First of all, this set of numbers. We cannot say that this list, if we were doing all this stuff, we can't say that it's normally distributed. But what we can say is if we do this, what I had you do over and over and over again, that the means of all the samples, that's what each one of your things were, was a sample of the numbers. The means of all the samples will be normally distributed. And then we can use that normal curve like we've been using this whole chapter to find probabilities that, you know, somebody picks this list, somebody picks this list, somebody picks this list, so on, so on, so on. So we can do all this, but we got to take the mean over and over and over again of our samples. And it's just a sample distribution. That's what we're going to cover today. What I want you to do next is I want you to take these and include my two. I want you to take all the means that everybody found and add all of them up. So I want the sum.
Wait, so you want us to do yours twice since Isaac did?
Yeah, just copy mine.
Yeah.
You know, making fun of Jenna and Isaac just copied mine.
Yeah, exactly.
That's what I was gonna do.
What is it?
68.8.
I got Abraham.
What'd you get?
Is that correct? Yes, no, maybe? So that's what all of them add up to. Now what I want to do, how many X bars did we have? How many means did we have?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I don't know.
There's four, and then there's
16 or 17. I don't know.
That should
1,
be
2,
16.
3, 4, 5, 6. How many was it? 1, 2, 3, 4, 5, 6, 7, 14, 16.
So it's 16? What we're gonna find is we're gonna find the mean of all these means. Alright, so in other words, we're finding the average of all those means. The way we do that, we take all of them added up, and we divide by how many of them were there?
16.
Somebody do that for us.
4.3.
Now, ours didn't work out great, but what we're gonna learn today is that this mean of all the x's, if we did it over and over and over and over even more, we don't have a very large population here, so that we can't really do a whole lot of them. But if I made you do it 2 more times each and we kept going, guess what would happen with this mean and this mean?
It's gonna get closer.
And after a while, if we did every single possible one of these,
It'd be 3.
it'd be exactly 3.5. Alright? And that's what, when we're doing sample means, and the distribution of these sample means, that's what's going to happen, and that's the main rule that we're going to cover today. So some of the assignment is really easy, because they're going to tell you this. They're going to tell you that the mean of the population is 7, and then they're going to say, what's the mean of all the sample means, and guess what it's going to be every time? The exact same thing. Those two are always going to be equal to each other. So when they ask you that question, easy answer. Another thing that's going to happen with these, if we were to graph our original set, if it is normally distributed, it's going to look something like this. The mean would be 3.5, that's right in the middle. When we do the mean of the sample means, what happens is it's still normally distributed, but the 3.5 is right in the middle still. But what happens is the standard deviation gets smaller. So instead of being like 3.5, and then if we add, we'll just say we'll round this off to 2.3. So the next one will be 5.8, 8.1, 10.4. And I'm not going to go out the other way because I can't subtract all that in my head usually. 2.3, that'd be 1.2. I can do that one. So on, so on, so on down. What happens over here is that standard deviation gets smaller. So now the curve looks like that instead of this. It goes up quicker. It's more smashed together. Okay? And what this allows us to do is when we don't have something that we can say is normally distributed, and we can't just use this, we can find all these means, these sample means, and we can make it so it fits that normal curve. All right? But we have to find all those means like we were doing here over and over and over again. Questions on the homework. Page 262, problems you want to see worked.
$34.
34. Kidney transplant waiting times. The time spent in days waiting for a kidney transplant for people 35 to 49 in a recent year can be approximated by a normal distribution as shown in the graph. So that's the one to the right up above there, right? What waiting time represents the 80th percentile?
Here's 62.
So we want the 80th percentile, P80. If we want P80, what is our probability that we're looking for? How do we change that P80 into a decimal?
It's just point eight.
0.80 or 0.8? So that's what we're looking for. We're looking for the 80th percentile. So if we're on our graph, and I always like to draw this graph, and I highly suggest that you do this. We got our mean here, whatever that mean is. We want something that's in the 80th percentile. Well, the mean stands for the 50th percentile, so we're over here somewhere. And we want the area going this way to be 0.80. And they told us the mean, I'm guessing, what was the mean? 1674? So I didn't have to write that, I could have put 1674 right there. We want where all the area is down this way. So if you're in the 80th percentile, you're at the 80th percentile, we know that the number of days that you're going to wait is more than 1,674. Using your calculator, because I don't have my calculator up here and I'm not walking back there and getting it right at the moment. If that's what we're looking for, we hit second vars. And then we go down to what, number 3? Is that right? The inverse.
Inverse normal, yeah.
Second large.
And this is the part I can't ever remember what we put in. I think we put in the area first. Is that what we said last time, 0.80? And then after that, we put in the mean and the standard deviation. Is that right?
Yeah.
Standard deviation this time was 212.5. Says inverse norm.
I got 1,852.
Does it make sense?
8.
So we'll say 53. Does it make sense that if we're out here, that person that's at the 80th percentile is waiting 1,853 days on their kidney?
Yeah.
All right, just looking here, it makes sense because if you were at the 50th percentile, you're waiting 1,674 days. So somebody at the 80th percentile is going to wait longer than that, 1,853 days. So this is one of those times, is it good to be at the 90th percentile? No, this time, and well, I shouldn't say it's good because now we'd rather be down here somewhere, but if you're down here somewhere, that probably means you don't get the transplant real quick, you won't have to worry about a transplant because
Or it means you've already.
you won't be around.
Or it just means you got like a common blood type.
That could be part of it.
Common.
Part B says, what weighting represents the first quartile? First quartile. Where is the first quartile located? How can we change that into a number that we can understand?
If you subtract that 212.5 a couple times.
So we could do it, doing that. When we were doing our graphs and we were doing quartiles, quartile means that you're splitting it up how? Fours, right? So you got 1, 2, 3, 4 parts. The middle quartile was the median for quartile 2, right? Quartile 1 is here, quartile 3 is there. Even though you got 4 parts, you only got 3 quartiles, because that's how it's splitting it up, right? We want the first quartile, the number that represents this first quartile. Well, what percent of the people are there or below?
It's like 2.25.
It's, for this, you're
25.
thinking of the other one, the empirical rule, you're thinking of when we split it up into the standard deviations. So this is 25, this is 25, that's 25, that's 25, right? Below this number is what percentage? 50. Below this number?
75.
For the quartiles. So that's the percentage below this. How are we gonna translate that into this? We want what's the area gonna be? 0.25. So now we're gonna switch this, and what are we gonna stick into our calculators?
0.25, 1,674. And then 220.
Before you punch all that in, should our number be higher than or lower than 1674? 74, and that's at 50, so I would guess it would be, almost like half or something maybe. Can't say that for sure, but
I got 1,530.
is it 1,530?
You could round it up to 1531.
So now that I think about it, it shouldn't be at half because we're only going down 212 each time, not. So you wait about 1,500 days, which is what, about 4 years?
Yeah, 4 years. I divided.
Oh, well,
Next question.
yeah, I mean, honestly, if not, you're close.
Oh, yeah. You're on, wait, 4 years, you're on life support.
Where did my case go?
36. Mine's at
36.
second, and it's not on.
Wow,
So it's not yours.
y'all took my case. Lost it.
Mine says, no.
Isaac, are you laughing because these are all even numbers?
We have to do 36.
Yeah, you did. No, I didn't.
I don't even remember. So. The annual per capita consumption of ice cream in pounds in the United States can be approximated by a normal distribution as shown by the graph. The graphs are there on the side. What's the largest annual per capita consumption of ice cream that can be in the bottom 10% of consumption? Well, if it's 10% on our little graph here, where's 10% going to be located at?
For the very left.
So it's over here, and we want this to be 10%, which as a decimal is what? 0.10. So when we go to punch it into our calculator, what are we going to put in? 0.10, then the mean, which they told us was how much does the normal human consume in 20.7? 20.7 pounds, and 4.2 is the standard deviation. Somebody punch all that in.
You got it, ice. Ice.
15.32.
So if you're in the bottom 10%, if you don't like ice cream a whole lot, and you're in that bottom 10% of all of them, you probably consume somewhere around 15 pounds of ice cream in a year.
I don't even consume that.
I don't even think
I do
you
either.
can, that cannot be the same.
I'm like,
Huh?
Cause like this will go with a while ago. I
I don't think it's the same. Just right now.
I barely.
That's a lot of ice cream.
Well, I mean, you got 365 days distributed.
I'm also lactose intolerant, so maybe that number just seems right.
Yeah, I mean, you got 365 days to distribute your kids.
Between what two values does the middle 80% fall? So this time we want, a little tougher this time. We want 80% of the data to be in here. What's that tell us about these two areas?
They're both 10%.
So they're both 10%. Well, we're only really gonna find one of them. We wanna find this one, which
It's 15.
we just found, right? Now, the bad thing with this is, we found it, if we were doing it in z-scores, the other one over here would just be the opposite of this number. But we didn't do it in z-scores, so we can't just do the opposite. What number can we put into our calculator to represent this spot going down? What percentage of the area falls from there down?
90.
So on your calculator, punch all this back in, but put in 90 and all that other stuff this time, or 0.90.
26.08.
And Lily, as quick as she got that done, probably figured out that she could just go back, second and enter and go back and punch it in, right?
Don't you have to subtract 53?
No, because what we were looking for is the two numbers where 80% of the area falls between them. So those two numbers is where it falls, 80%. Now, if we go back to check to make sure our answer is correct, going back to the previous section before this one, we should be able to put in our low limit, our high limit, our mean. This is what we did in section 5.2, and our standard deviation. Do this, but not inverse norm. We don't want inverse norm. We want the CDF one, the one right above it, number 2. And what's that give us? I'm hoping, unless I'm completely wrong,
0.8. No. Yeah.
should be something real close to that. That's what we're looking at, right? 80% of the data is between those two numbers. So this is what, doing this is what we were doing the last section. Now we're actually finding the numbers instead of, so here they gave us their last section, they gave us numbers and said, find the area between these two numbers. Now they're saying, here's your area, find the two numbers. So it should have worked out that it's about the same, that 80% or 8.80. Other questions? Are we done? So what we're going to cover today, sampling distributions and the central limit theorem. All the central limit theorem is sort of what we were doing there. We're saying we could have some graph, whatever our graph looks like. Maybe our graph looks like this. Who knows? We can take that graph and we can switch it into the normal distribution by finding a whole bunch of means, like we just did at the beginning of class there. And all those means will end up being really, really close to the mean of this set of data. So what we're going to cover, sampling distributions, dealing with their properties, interpret central limit theorem, apply central limit theorem to find the probability of a sample mean. That's nothing. That's just what we're going to cover. Sampling distributions, this is where we really start at. Not too far. So sampling distribution, the probability of the distribution of a sample statistic is formed when samples of size n, so that's our size, our n, how many you're taking at a time. When you guys were doing it, at start, your n was 5. You took 5 numbers at a time. And you repeat it over and over and over again. And it's called the sampling distribution of the sample mean. And I think the abbreviation for that, I don't know why I don't have it on this PowerPoint, and we use it somewhere else on down the line. I think it's this, SD. That's not right. Sample means. I think it's SD mu x bar with the subscript there. Something like that, I don't know. We'll find out on down the road when I actually have it on the PowerPoint, I guess. I can't remember the symbolization for it. So hopefully I don't have it on the next symbols test.
What's up?
What, that? Is it N?
Because I can't get, it's a mu.
Mu?
Is that the same sign we have for the limit of the unit in zoology?
What?
There's a mu and it's the same unit.
Micrometers.
Yeah,
You use mu for micrometers?
I think,
Well,
yeah. It looks like it.
microscopes. It's the same thing.
Okay.
Cause he said it was new. It just means a different thing.
It's just like any other variable. X in algebra doesn't mean the same thing that we're letting it stand for in here. It's just a variable. It's just a abbreviation or something that represents something else.
I hate that when one letter, I'm in zoology, like micrometers, and I get that here, and it's like, you know, like, why? Who decided to put letters in that?
It's,
Michael, if you haven't figured that out by now, then it's got nothing to do with the letters. It's just something to stand for something else.
Yeah, no, but like,
So if you don't like letters, I do this with my transitions math class all the time. Because last year I had a student in there who hated it every time I made it algebra. So it says something like, the sale price of an item is the regular price minus the discount amount. So I would be stuck doing this all the time. Regular price minus the,
just kind of, instead of putting like,
instead of putting discount amount here, it would have to be, or I would put like percent times regular price. Because if we're taking something off.
yeah.
So I would have to write it out in words like that for them all the time instead of saying regular price, okay, we're gonna let that be R. And then we got some percentage, 20%, so 0.20 times R, and it makes it a whole lot shorter and easier to look at.
Yeah, I mean, like, I understand that, but like, I just,
That's all
yeah.
this stuff is. So it's making it shorter instead of, it's not like it's letters in math, it's something to stand for something
Yeah.
we don't know. Key ideas on this. These are the 2 key things that you got to know today. When you take the mean of the sample means, which is mu with the little subscript x bar, guaranteed that symbol will probably be on the next symbols test. That's the mean of the sample means. Mean of the sample means. Just because I like it and it confuses everybody, because every time you say it, you think, what? Mean of this, what?
I mean, it makes sense because you have two mean symbols next to each other.
So you take, all it stands for is, you're saying, you're finding the mean of all the means. You're finding the average of all the averages. So on that stuff that we were just doing, that you did on the board a few minutes ago, you found your mean, then we took all of those means, add them together to find the mean of that,
What will that
of
mean?
all the samples.
Mean.
Those two formulas, main thing today. First one's real difficult. So probably the hardest formula we've had all year. So if Braden gets stuck on it,
We have a problem.
yeah. That's one I was talking about at the beginning. When we found the mean of all those, the original population, it was 3.5, then the mean of all of your samples, if we kept doing it over and over and over again, should be 3.5. This is called the standard error, and this is another one of those that I'll probably screw up, and I've already done it at least once today. It's when it's sigma and x bar is the subscript, it's called the standard error of the mean. I'll probably call it the standard deviation, which it's not supposed to be. But notice, the standard deviations aren't the same.
Computers are tricky.
And the other thing I'm going to say about this number should be smaller than whatever the standard deviation was of the
So is this like,
population.
is this whole thing called the standard error or just like the second one?
Just this, that right there is the standard error.
Okay.
That symbol. This is how you find the standard error. That's the formula to find the standard error. Remember, this is the standard deviation of the population or the original set. N is how many you take at a time.
So on our quiz test, how do we call it the standard error?
Unless I keep screwing up calling it the standard deviation, then I'd probably accept that also.
Okay.
So if you put the standard deviation of the means, but this is the standard deviation of the population. This is the standard deviation of a sample.
So if we just put standard error, would be fine?
Yeah.
Okay.
This is sort of what we just got done doing, same idea. We go through here and we find all this different stuff. They went through, they found it all out longhand. We would probably use our calculator to find it instead of using all of this. You graph it. When you graph it, this time what happens is all the values came out the same. Does anybody remember what that's called?
Can anybody remember what it's called?
I didn't even see the
Year.
graph that you covered up because I was trying to get rid of the word.
List all the possible samples. We were going to go down. One of the problems on your homework has you do this, where they list all the possible samples. I got rid of one of them because one of them I started doing it and I thought, that's too much writing. So you list all the samples, just like we had up here. but you gotta do all the possible, then you go down through and you find all the means of those samples.
That's a lot.
And then once we have this, just like we did at the beginning, if we add all these up and then divide it by how many of them there are, that mean, and it probably says that on the next thing, that's our probability distribution. So the probability of you picking a sample that was 1, about 6%, probability of picking 2, about that. Notice that. Should notice that they look similar, some of them. And if we graph it, which you'll probably do here in a minute, we found the mean of that. The mean of all those samples was 4. The mean of the original set of numbers was 4. Notice here though, that's the variance, that's the standard error, then would work. That's the standard error. That standard error ends up being smaller than the original standard deviation. And what that does to your graph, your original graph looks like this, like the normal curve. The second one's a normal curve, but it gets sort of smashed in, so everything gets closer in there to that mean. My pen not working. Graph the histogram. Looks normal. This is the histogram for all of the X bars, for all the means. Not the histogram of the original. The original histogram, remember, looked like this. And I'm not sure why the bars weren't touching in that original histogram, but they all looked, it was uniform. Central limit theorem. What the central limit theorem does, it takes a graph that might look something like this. This isn't normal. And if the sample size, if our n is greater than or equal to 30, so we always need a sample size larger than 30. And we know the mean and the standard deviation of that population. The central limit theorem says we can find a bunch of sample means, so we can take a bunch of samples from this, find the means of all of them, and instead of the graph looking like this, the graph is going to look like the normal curve. So even when data is not normally distributed, we can take means, take means over and over and over, take samples and take means of all those, and we can make it so it's normal. All of this is the key to, I can't remember the word now. I'll remember it here in a second. Anybody remember all the different kinds of probabilities that we said there were at the start of the year?
Swans with a T, right? No?
Maybe.
Isn't it like the one where it's like every 5th person and all that kind of stuff?
No, that's how we get the samples.
I was gonna say, I like the ones with things.
Inferential. I couldn't think of the word. When we talked about inferential probabilities, the probabilities that they use to see like how much they're going to charge you for your car insurance, how much they're going to charge Ebersol for health insurance or life insurance or something. You guys can go out and buy life insurance right now. Good thing being your age. You buy life insurance, and Isaac can probably get $1 million life insurance policy right now for like $10 a month or something. Eversole goes out and buys it, and it's gonna cost him like $2,000 a month.
So would it stay $10 our entire life?
Yeah, but they don't run for your entire life. They usually, after a while, they cut you off. There's different kinds of life insurances.
Well, life. Would it be like?
Yeah, but it's like term life insurance, so they'll tell Isaac, hey, we're gonna give you this for $10 a month for the next 10 years.
So I gotta die within those 10
Right.
years.
Or after 10 years, you go back in and you renegotiate, and now they're saying, nah, you're not paying $10 anymore. Now it's gonna jump up to $50 a month, because now you're older and you're probably better chance you're gonna die.
Well, I think,
Wow.
better die in 10 years, if you're getting that.
I'm just gonna.
And there's things like term, there's whole life insurance. That whole life insurance, I think, and I'm not an expert on this at all, but whole life insurance is for your whole life, but that, they're not gonna give you a set thing. They'll say, okay, this is how much it costs, and then after a while, they're probably gonna raise the price on you a little bit at a time, and
I'm taking me and all my red front money to the grave.
You were the man for that, you know?
so when you're looking at this was not normal. When we take all these samples and find the mean of each of those samples, then we can make a curve that is normal. Our sample size needs to be greater than or equal to 30 to be able to do that. Otherwise, it doesn't work out. If our sample size is too small, like with you guys, when we did it up here, we only had 16. That's less than or equal to 30. It didn't come out so well. We were like 4.3 and we should have been at 3.5. So we needed a bigger sample size. The second part of the central limit there, if the population is normal, then you don't have to have any special n. So n can be anything. N doesn't have to be greater than or equal to 30. If the original stuff is normal, then n can be 10. So when you're reading these problems, that's one of the things you need to look at. What's the sample size? What's n? If n is 30 or more, we don't care if it's normal or not. It's going to work out. If n is less than 30, then they need to tell us that our original set of data was normally distributed. Is Cody ever going to come back on Orange Days?
Probably not.
Man.
Did you get in trouble?
No.
Is Mr. Wendell that mean to him?
I guess so. He's trying to go online, I
Is
I haven't seen Cody.
think. He'll show up tomorrow.
You will?
Yeah.
You don't
He was here yesterday.
He comes every other day.
Do they turn his stuff in still?
I don't know. Episodes just keeps dropping.
he? Haven't heard anything from him. Keep sending emails all the time.
Yeah, he's a nerve
But he doesn't turn anything in.
If he's like my other students, I've all the emails I've sent out this year, I think I've had 4 students who actually looked at it and said, sent me back anything or did anything with it.
I look at your emails.
Thank you. I appreciate that. Makes me not want to cry so much now.
I see him pop up on my phone.
Because sometimes I like.
Besides, sometimes, are
Sometimes
you like
I
up
use
at the
that.
crack of dawn? Cause I get
Like
on, like,
5:40.
sometimes when I get up in the morning, I look at my phone and be like, 4:30 in the morning.
This is what we did at
sent
class
this out, and
today.
I was like, what is he doing? He's up and at 'em.
Looks like,
He's before the crack of dawn.
Literally, he is the
He,
crack.
he wakes up the rooster.
He sees the crack of dawn.
He is the sun that rises. He wakes up the sun. Either that or he just doesn't sleep.
In the central limit theorem, I wouldn't write any of this down, you've already written this part. In either case, the mean of the sample means has to be the same as the mean of the population. Alright? The sampling distribution is always going to equal, or the variance is always going to equal 1 divided by n. We didn't write that down because we haven't used variance for a while. We haven't even dealt with variance for a while, as far as using it for anything. But notice, on the other formula, my pen will work. The standard error is standard deviation divided by the square root of n. Well, the variance of anything is just the standard deviation, or the square root of the standard deviation, or you take the square root of this to get the standard deviation. I knew what I wanted to say, couldn't think of how to say it. That's ugliest sigma probably ever made. So, all you're doing on this is, if you notice here, that's supposed to be squared. Well, if we take the square root of that, that just gives you sigma. All you're doing is dividing that by n. Well, we're dividing this by the square root of n. So we're just taking the square root of the whole variance thing. So that's nothing different than what we've ever done, but we just don't deal with variance as much now, so I'm not even going to mess with it.
Could you give it a 1?
I could have just popped it up there. Again, any population, if your graph looks like this, we can't do a whole lot with that. We can't find the area between here and here and say, hey, this percentage of the stuff's going to fall in there. It just doesn't work. But if we can change that into this normal curve by taking a whole bunch of means of different samples, then we can change it into this. Cell phone bills for residents of a city have a mean of $63 and a standard deviation of $11. Random samples of 100 cell phone bills are drawn from this population, and the mean of each sample is determined. Find the mean and standard error of the mean of the sampling distribution. Then sketch the graph of the sampling distribution of the sample means. So notice, this is our n. This is our mu. This is our sigma. And all we're going to do is use those three to find this. And if we look at the original graph, it looks sort of normal, but it's not exactly normal. To find the mean of all the samples, the mean of all the sample means, it's the same. So 63. So that part of the answer is easy. To find the standard error, that's the equation. We have to do this. We have to take whatever the standard error was, or the standard deviation was. I believe it was 11, right?
Over.
And we divide it by the square root of n, which was 100. So we divide it by that. Well, square root of, and some of this you can do in your head sometimes. They make it easy for you. What's the square root of 100?
10.
And then 11 divided by 10 is
1.1.
1.1. So now when we go to graph this, the original graph looked like this. It didn't look like this, but because it wasn't normal. But it had 63 right in the middle. Then it went up by 11, 74, 85, 96, went down by 11, 52, 41, 30. So it was like that, but it wasn't, it was all crooked. When we go to graph this using this, now it's going to be normal. I don't know why I do that every time. Our mean is going to be 63, but now our standard error is 1.1. So we go out to 64.1. Then we go out to 65.2, and so on. Notice what's going to happen here. All of this, everything that I'm doing on this side, 66.3, is falling right in this little area. So the graph's going to actually look something like that.
So how far will it go out?
But it's going to be normal. It still goes out 3 standard deviations this way and 3 standard deviations
Next
this way.
shot, 3.
But so on this graph, it's going to actually end up looking something like that.
A lot smaller.
It's a lot smaller, a lot more compressed. But what we're saying there is if we take a sample from this set of people that have these cell phones, and we just do it over and over and over again, we should get in that area there most all the time, if we're taking the mean of a sample. Now, are we going to get people who are way out here somewhere? Yeah. Are we going to get people who are way out here somewhere? Yeah. But if we take the mean of all of those as we put them together, we're more likely to fall in here. So if we do a sample and we come up with our mean of our sample is 87, that's very unusual because we're way out here on the normal graph, and that's going to miss this graph completely. So that would be very unusual to find a sample that has something way out there. So that's what it looks like. See how it's real spiked, but it's a normal curve still, even though it doesn't look like my normal curves. And this is where I told you at the start of this chapter. When I draw my normal curves, I draw them like this just about every time, and I shouldn't. Because sometimes they're more compressed, other times they're more spread out. Suppose the training heart rates of 20-year-old athletes are normally distributed with a mean of 135 beats per minute and a standard deviation of 18 beats per minute. A random sample of size 4, so that's our N, and it's less than 30, but it says that they're normally distributed, so that doesn't matter. So this time they're normal, so the curve looks normal. Find the mean and standard error, so on, so on, so on. So if I find the mean, first of all, the mean of all the sample means is going to be the same thing, which was 135. And then the standard error is going to be, what was it, 18 divided by the square root of 4. What's the square root of 4? What's 18 divided by 2? So now this is what we're looking at. If I'm doing it on this graph right here, we want 3 standard deviations that way, 3 standard deviations this way. 135 plus 9 is 144. 135 plus 9, or 144 plus 9 is 153. I didn't draw this very well. 153 plus 9 is 162, so it's going to actually be out there somewhere. The 153 should be more over here. And I could go down this way and do the same thing. So it's actually going to look, it didn't go up that high. It's going to actually look something more like that. It's sort of a little more in. But now we're saying that everything should fall in that range somewhere if we're taking these samples. Let's see if we did all that right. 9 is the sample error. And then it just looks a little more compressed. So now if we go out and we pick 4 20-year-olds, and we take the mean of their heart rate, and their mean falls here somewhere, that's possible.
But
It's very unusual that all 4 of them fell that far out. Might be something where we're a little worried about them. Maybe they're using something and they're just too mellowed out for some reason. I
I
don't know.
wonder what that is.
Yeah, I don't know.
wait, did that say heart rate? That's not even a healthy heart rate though.
For 20-year-olds.
Is that still in heart right now?
Huh?
I don't know, does that?
Well, your
Did you
heart
see
rate
Patrick
should be
Mahomes?
slower than
Huh?
No, I
mine.
meant like smoking doobie.
His heart rate was highest when he did not have the ball, but when there was 13 seconds left, his heart rate was his slowest the whole game.
Does
I
that
don't
make
know.
your heart rate go faster or slower?
I don't know.
But like,
'Cause I feel like it calms you down.
I thought maybe you guys could tell me.
Well, Jim,
Smoke
that's
weed.
Well, normal heart rate.
Couldn't trick her, could we?
Normal heart
George
rate is
Ford,
not
you
right.
probably kill me.
My heart rate right
It's
now.
like my dad was probably.
It's
70%
74.
Back in the day. I know grandma was, so. She was.
Is that why she's
Becky's
She needs it
now?
now.
Crazy now.
I don't
That's why
remember-
she's so crazy.
I don't
now.
remember your grandma ever doing anything like that.
My dad told me one time.
Maybe she didn't.
He thought my grandma was poor when he was little because he thought they were all sharing the same cigarette.
It was not.
And I don't know, but
She needs it. We're trying to get her a medical card.
your grandma's always been a.
Whack job.
No. She's just very outgoing, very.
She's always been like that.
Yeah,
There's
she's
no way
always
she's
been
been.
like that.
She hasn't been that how she is now.
Yes, no, she was always that way. She was always very outgoing, very.
Lord.
I will never forget the day Jenna didn't tell her we had a game. She kept saying, "Let's go, Liza!" So we had to practice. Yes.
She's probably sitting in the gym right now waiting on the game.
She's got to be the first one there.
If we wanted to transform from our raw scores to our Z scores, we'd use this formula. We're probably not going to do that, so I'm not going to have you write this down. Most of the time, we're going to be using the calculator. I think this next slide gives you what you punch in on the calculator. So if we're finding area of probability on the calculator, second bar is normal CDF, lower limit, upper limit. It's the same as what we did, not last section, but 2 sections ago, except now instead of putting in the mean, you're putting in the mean of the sample means. And you're putting in the standard error. And I forgot, do I need to put this in there? There's a comma here. You guys know to put those commas in, right?
Yeah.
Comma.
And if I forget, we'll find out when we're there.
Yeah, as soon as you punch it in, it says error. You know, oh, I forgot the commas.
Bengals win, for sure, so we have it.
And in the beginning, so we
Like, go to school next day.
Did you get money from your dad last weekend?
Our volleyball senior.
No. I got a bag in for $5.
You're not asking at the right time.
He's like, do you really
I
need it?
might be, but I don't think.
Yeah,
Different
I have
puts on.
0 gas in my car. Go ask your mom, she's got it.
But at least that's good, because I swear I had $5 in my wallet 2 days ago, and then yesterday I looked at my wallet, and there wasn't $5. There was a $1 bill instead of a $5 bill.
But we were really good sophomore.
Hey, on Waterman.
Or junior.
Money's depreciating while it's in my wallet, I guess.
Did we win?
You're losing money while it's sitting in your wallet.
But I was out there somewhere.
The graph shows the length of time people spend driving each day. You randomly select 50 drivers aged 15 to 19. What's the probability that the mean time spent driving each day is between 24.7 and 25.5 minutes? Assume that the standard deviation is 1.5. Notice, this sort of looks like, this sort of looks like a normal curve if I could draw it. So what we need on this, and they tell us the average over here, we're looking at 20, or pages, 15 to 19. The mean is 25, 25. All you're going to do is punch this into your calculator. On your calculator, we're going to punch in the low limit, not that, low limit 24.7, high limit 25.5, the mean, which is 25, and the standard deviation, which is 1.5. We punch that into our calculator, we're doing we just want the area so we don't have to worry about any of the rest of that stuff. 2.1. So about what percent of people your age drive between 24.7 and 25.5 minutes a day?
21.
About 21%.
Me, every day.
All right, so that's the people who fall in that range. You may drive more, you may drive less, but that's in that range.
I wanna have it.
Well, that's not you.
Huh?
That was
21, they got 0.21213. They changed all theirs into Z-scores, which seems like a big waste of time. Education and Finance Corporation claims that the average credit card debts carried by an undergraduate are normally distributed with a mean of $3,173. Probably most of you, if you go off to college and you got a credit card and you build up a $3,000 credit or $3,000 on it, you're probably gonna come home and get shot. And a standard deviation of $1,120. What's the probability of randomly selected undergraduate whose credit card has a balance less than $2,700? So as we're punching in our calculator, we'd want $2,700 or less. Your low limit, remember on your low limits, punch in something like negative 10,000. If we're just going from there down. If it was a high limit, if we were going up, then we'd put in the 2,700 and then a high limit of like positive 10,000. There's my pen doing this. So we're looking at this. Again, they change it into Z-scores, which is worthless. And about 33%. Run through this.
Where's my cover? Who got me on my book bag?
You got out of your book bag.
Never.
Yeah.
Did you look in your book bag?
It was laying on your, like your calculator was laying on your
I'm
desk.
not even checking it.
Your assignment, page 274, 1 through 21 all, 25 through 41, the odd numbers. On the 1 through 21, skip number 11. Number 11, number 12, sort of the same kind of problem, but skip number 11.